So section 6.3 is on page 387, talks about arc length, a very important idea that we need to really get down and grasp. Suppose I would like to find the length. Let's pick something that changes, sine will do, or cosine, it doesn't matter. So let's say you're looking at something that keeps on changing non-stop. It doesn't have to be a sine, it could be anything. But the point is, I'd like to find, let's say I want to find this length from A to B. And this is the deformed function. It's not really a sine wave or a cosine wave, you know, not something that's measurable. So what I do, if I want to find the length of this piece, what I do, I split it up into pieces. I break it up into tinier pieces. And what I do, I run at it straight. Now you could tell it's not straight. That is, if I take this piece right here and I blow that up, what I'm really trying to figure out is actually this piece. But what I'm using a straight line. If I called this small piece right here the change in S, right? Where S is the length of where delta S is the length of the piece of wire or whatever that is, what that will generate a delta Y and a delta X. And if I look at this piece, let's say right here, the piece looks like this. This is really what I'm trying to find. What I'm using instead, I'm using a straight line. So I'm taking this, calling that delta S, right? And again, if you really think about it, if this is delta S, associated with that is a change in X and a change of Y. So I could say that for each one of those pieces, I could say delta S squared is delta X squared plus delta Y squared. So keep in mind, this is not the piece that I want. The piece that I want is this green. So I'm approximating here. I'm using that small straight edge thinking, well, it's really small. Let's make it really small. And the straight line and the arc will match. Right? And then when I look at this, say, wait a minute, but I could, if I want, divide everything by the X squared. So wouldn't that be so I could have divided everything by the X squared. Just simple algebra. It's important to understand this. So when the derivation come up later on in your next math course, you are very comfortable with the notation and you really understand it. And can't I say ds dx equal the square root of 1 plus dy dx squared? And if I cross multiply, wouldn't you say ds is the square root of 1 plus the change of y with respect to x squared times delta x? Or can't you say, you know what, forget that, I want to divide by delta y squared, not delta x squared. And I'll tell you what that means in a minute. So this will be ds dy squared equaling dx dy. Again, those are length, right? And I could say ds dy equals the square root of dx dy squared plus 1. In fact, cross multiply. So which one is it? Is it the first or the second? Well, it doesn't matter really. It depends on the curve and how you want to do it. And as we know, for approximating ds, we really use not delta. Delta is the exact, this is the approximate. Remember? 5a when you did approximation, and ds could be the square root of dx dy squared plus 1 dy. So ds is either 1 plus y prime with respect to x or x prime with respect to y. Now, what you want to get out of this section is figuring out whether to do it in terms of x and y, and there's no wrong way of doing it. There's easier or harder way of doing it. But now, let me elaborate on one thing that I left out. Now that we have this, I'm going to shrink this just a bit. It's way too big. I'm taking a lot of space for no reason. I could have put it right there. There we go. And I could have... Let me get rid of this and move this to the left, and let me show you something really quick on the other. So that's really what we got out of those. Now, if I look at this, I could say in this case, if I want the length of this curve, why is that not erasing? Wow, that's, oh, it's not there. Ha, just kidding. So, if I wanted to find L, do you see that that would be delta S1 plus delta S2 plus delta S3? I never mentioned how we went from this to this. I just said you learned that in the first semester calculus when you showed the exact versus approximation. So I could say L equal the series n equal 1 to infinity of delta S sub I, wouldn't you say? And if I take the limit as n approaches infinity of the series n equal 1, I'm thinking ahead of myself, right? I equal 1 to n. Oh boy, I just taught this class, so I'm stuck with the n. You'll know by the end of this class why that is. And wouldn't that be the integral from a to b of ds? And that's by the definition of the Riemann sum. So, if I want to figure out what L is, L equal the integral of ds. And there it is. So, I'll look at some problems and I'll show you, you should really pay attention to how to do this. And that'll save you a lot of pain in the next section and later on when we get to chapter 10. So if I look at problem number 2, and now I'm looking at page, these will be on page 391. So remember, if you get this section, the next section will be a special case, really easy. If not, the next section that has 8 formulas, we're going to skip all of those. It says, find the length of the curve. No need to graph it. So I know that L equal the integral of ds. The question is, should I proceed with the x or the y? So this is how I decide. When I decide how to do this, it's a square root of 1 plus, I'm going to square. You glance at what you have and you figure out, well, let's see. If I'm going to run, this is in terms of x. Is it easy to take a derivative in terms of x? If that's the case, then you choose x. That's how you decide. What's the derivative? Because that's what this is. The derivative of this would be what? Y prime is 3/2 x to the 1/2. 3/2 x to the 1/2. And I'm going to integrate that from 0 to 4. Make sure that if this is dx, then it's x equal to x equal. Now, set up, do not solve. There it is. You're done. Right? And in these problems, they want us to set up most of those. Or you could solve them as a practice for what we learned in chapter 8 so far. There is one more section to go in 8. I have 2 of them actually. 8.8 and 8.1. But I want to get this out of the way now that you could do it. If I look at the next problem on the list, yeah, that's where I keep my stash. And if I take this problem, well, again, find the length L equal the integral of ds. Any of these problems you can't work out by hand, let me know and I could work it out for you. So when I look at this, I notice this is in terms of y, this is in terms of y. Even if I want to solve for x, that's a lot of work. So it would be easiest for me, again, this is how I decide a derivative squared, and in this case delta y. Since this is delta y, I could put y equal 1 to 9. And what's the derivative? What would x prime equal? So bring the power down, 1/3 times 3/2 y to the 1/2 minus 1/2 y to the negative 1/2. So those cancel out. This will be y to the 1/2 over 2 minus 1 over 2y to the 1/2. Now this problem I do want to work out. This is a new type of integral that we haven't seen before, but it's important that you keep track. 1 plus, this is, if you square it, that's y over 4 minus 2 times, if you multiply those, that's 1/2 plus 1 over 4y dy. I do want to point one thing out. This square gave this. And can you tell what happened from top to bottom? If you take 1 minus 1/2, isn't that 1/2? And do you notice what changed? This was a minus. Now it's a plus. But do you see that this is identical to this? Doesn't that make it the integral from 1 to 9 of the square root of? And wouldn't that go back to y to the 1/2 over 2 plus 1 over 2 y to the negative 1/2 squared dy? And that trick we haven't learned yet because it didn't come up. You're not responsible to know that this is a perfect square, but the fact that you got from this to this and here to this, you should be able to go back. And wouldn't that be simply y to the 1/2 over 2 minus 1/2 y to the negative 1/2 dy? And now you simply add 1 to the power and proceed. So this is a new trick that we're going to learn. Everything you learn in this class will come up in the next class. Every trick. Couple of more problems to set up. So if I look at problem number 6, the same deal. I look at that, say, okay, well, let's see how that works. Well, I'm going to say L equal the integral. It's 2 to 3, the square root of 1 plus. And what's the derivative? Bring the power down, subtract 1 from the power. And isn't that negative 1/2 y to the negative 1? Wouldn't that be plus 1 over, actually, I'm going to make that a plus. Again, I made those up. I didn't think about them as much. Now that I'm thinking about it, it's going to be, when you bring the power down, it's going to be negative 1 over y squared. And the same deal happened again in this section. This comes up a lot. If I take 1 plus, isn't that y to the 4th over 4 minus twice, if you multiply those, 2 times 8 times, oh, there was a 2 there. 2 times 8 times b, isn't that 1/2? Plus 1 over 4y to the 4th. And again, it happens again. Computer's acting up. I bought another one, but I didn't change it yet. So wouldn't that be the integral from 2 to 3 of the square root? And notice, again, this perfect squared gave this. And look what happened. That's y to the 4th over 4 plus 1/2 plus 1 over 4y to the 4th. If this gave this, can't I go back? Wouldn't you say that this will equal the integral from 2 to 3 of the square root of y squared over 2? I'm just copying this with a plus. 1 over 2y squared dy. And the square undo the radical. That would be the integral from 2 to 3, y squared over 2 plus 1 over 2y squared dy. Add 1, divide by the power, and add another 1, divide by the power. And that takes care of the problem. So this section, you start with, almost forgot. and I have one more to go. It's a bit messy, but we're going to set up. Anything you want me to integrate, I'll be more than happy to integrate in class. Keep in mind, on the homework, some problems they say set up, do not solve. That means the integral is a bit challenging. Another reason for choosing a dx or dy, sometimes you can't integrate. Not going to happen for you guys. But in that case, you switch the order. So L is the integral of ds. In this case, it's obvious I can't solve for x. So I'm going to say that's the integral from x equal to x equal. So I'm going with dx. 0 to 2. The square root of 1 plus, if I take a derivative, isn't y prime 3x, so it's x squared plus 2x plus 1 plus, I don't know where that came from. Why would I even want to do that? You know what? I apologize. There. Let's say that's the problem, right? And make things easy. Again, we're setting this up only because it's does set up. Say set up in the what happened to those? How did they oh yeah, I took a piece out. So wouldn't that be x squared plus 2x plus 1 squared dx? And on a test, if I say set up, do not solve, and I do that a lot in this class, this is all you need for those. I'll ask you to integrate chapter 8. Once you do that, the majority of what we do after is really set up. Let me get you the homework. And there's the homework. And that concludes this section.